Good afternoon everyone and welcome back to Real Numbers. Before moving on, don't forget to subscribe to our channel and click the bell icon to receive notifications. Now in the previous class, we discussed Euclid's division lemma and how to use the Euclid's division algorithm to calculate the HCF of two numbers. Now in this class, we'll first be looking at something called the fundamental theorem of arithmetic. And before moving into the actual theorem, I want you to briefly look back into something you have already learned called prime factorization. So prime factorization, you already know what it is. It's simply breaking down a number into all of its factors. That is, say 24 for example. What you do is you find out which prime to divide it by. Say 24 easily divides with 2 and you get 12, which you can further divide by 2 to get 6, which you can further divide by 2 to get 3. And now you write 24 as a product of these factors, that is 2 into 2 into 2 into 3. And that's pretty much all there is to prime factorization. You can write it as 2 raised to 3 times 3. And say if you use another number, let's say 91. 91 is an interesting number. 91 is an interesting number because it does not go in 2, 3 or 5. You can divide it with 7 and you'll get it is 7 times 13. You can try it out yourself, you know all of this. There is no surprise here, but I want you to notice something else that's very interesting. That is, 24 can be expressed as 2 into 2 into 2 into 3, and it can only be expressed as a product of these specific prime numbers. That is, 24 can only be expressed as 2 into 2 into 2 into 3. I mean, you can rearrange them like 3 into 2 into 2 into 2, but still the prime factors can only be 2, 2, 2 and 3. And also 2, 2, 2 and 3 when multiplied together can give you only 24. This might sound very obvious, you already know all of this, but surprisingly that is all there is to the fundamental theorem of arithmetic. So let's look at the statement and it will become very clear. The fundamental theorem of arithmetic simply states that every composite number, in our case it was 24 and 91, it can be expressed as the product of more than one prime numbers. Say we express 24 as 2 into 2 into 2 into 3, more than one prime numbers. We express 91 as 7 into 13, there are two prime numbers here. 13 is a prime, as you know. So it can be expressed as the product of more than one prime numbers, and this factorization is unique. That is, 24 can only be expressed as a product of prime numbers in this format, that is 2 raised to 3 into 3, and 91 can only be expressed as a product of prime numbers as 7 times 13. Very easy. The last point is pretty obvious. Apart from the order in which the prime occurs, I mean, we all know multiplication is associative. You can move around the factors in any way you want, but the prime numbers can only be these numbers. Say 24 is 2 into 2 into 2 into 3. It can be 3 into 2 into 2 into 2, but the prime factors are the same. And that is the fundamental theorem of arithmetic. Now we'll be using the fundamental theorem of arithmetic to find the HCF and LCM of two numbers. This is nothing new to you, you already know all of this. And say for example, if I give you two numbers, say 56 and 252, say for example, you can immediately use the division algorithm, which you already know, or the other way is to factorize them. And let's factorize them first and see. 56 I can write if I just draw a factor tree. I mean, you might not prefer drawing a factor tree, but it makes things seem easier. So let's draw a factor tree. So you can write 56 as 2 power 3 times 7. And in a similar fashion, you can write 252 as and 256 can be written as 2 raised to 2 times 3 raised to 2 times 7. And to find HCF is very easy. After you factorize, all you have to do, as the name implies, highest common factor. So you just have to rule down the common factors. So if I just write them down like this, it will look much easier. So here the common factors are 2 times 2 appears in both of them. There is an extra 2 here, but we can't consider it since it's not common. And there is a 7. So the HCF simply turns out to be 2 times 2 times 7, which is 28. And the LCM, you know the strategy to find the LCM. Let me just recount it for you. You have to find all the factors of both these numbers. So in our case it's 2, 3 and 7, and you have to pick from which of the two numbers these factors appear the most amount of times. In our case 2 appears 3 times in the first number, so we are going to pick that. So it comes as 2 power 3 here. 3 appears twice in the second number, that is 3 power 2 here, and 7 appears in both of them but only once, so that's just 1 7. This will come out to be 504. But I think you know the drill to do all of this. I'm not going to elaborate into it. Here we are going to learn a small relation between the HCF and LCM to make these things easier. Here is a formula. Two numbers A and B, and the highest common factor of A and B multiplied by the lowest common multiple of A and B gives you the product of the numbers themselves, that is A into B. And maybe it's immediately clear to you how you can actually use this. The only problem with finding the HCF and the LCM using the fundamental theorem of arithmetic is that LCM takes a little more time. That is, you have to first write them out, then find each factor and find the most of them, and then multiply them together, which might be a little arduous in different cases. Let's actually consider a simple example, not the previous one, but a simpler one maybe. Let's say 24. I like 24. And then let's say 52. 24 is 2 power 3 times 3. And 52, if you factorize it, it will come out to be 2 into 2 into 13. Now, given this, you can immediately factorize them. You can find the HCF that way. HCF will turn out to be, if you have two 2's common, and that's all. So the highest common factor will come out to simply be 4. And the lowest common multiple, to find that, you have to find each factor. You have 2, 3 and 13, and there are 3 2's here. So the LCM will be 2 power 3 times 1 3 here. So that will be a single 3, and then 1 13 here. So that will be a single 13. Now with all of this together, you can try multiplying them together and you will end up getting 312. But again, it might be a little arduous. You can do it, of course. But a simpler way, if you observe the formula, we can rearrange the formula and we'll get it to be LCM equal to A into B by HCF. Now, if you just look at it, this becomes very easy. A into B, as you already know, is 24 into 52. And the HCF just happens to be 4. I don't even have to multiply them together first. I can actually cut 24 and 4 first, or 24 and 52 first, either one. They will have a common factor. You will always be able to cut them since the highest common factor is a common factor of both of them. So you can cut them. With that taken care of, I will get this to be 6 times 52, which is naturally 312. So indeed it is true, the formula works, and it can usually make it very easy for you to find the LCM once you find the HCF. But pay attention that this will not work if you had another number, or in fact it will not work for any number of numbers more than 2. And in fact, you might find some formulas online or in some material which discusses what formula you can apply when you have three numbers. But I think personally it's much easier if you simply write them down and go with it simplest way. That is, you can just write their factors down, then find the common factors to find the HCF, then find which of the factors appear the most and multiply them together to find the LCM, and that is the best way in this context. Moving on. Now, another application of the fundamental theorem of arithmetic is something called digit prediction. It's actually just nothing at all. You can see very obvious equations on the screen. And the point is that once you know the factors of a number, you can actually find out how many zeros follow the number. And that's all there is to it. And the concept is very, very simple as well. Let us actually just take a random string of numbers and multiply them together and see how many zeros it will have in the end. So let's say you have 3 into 7 into 2 into 12 into 15 into 5 into 31. Random numbers. I just pulled it out. And I can directly predict how many zeros this number has following it by looking at the previous two equations. That is, say this 31 is just a random example. You just kept it there. If you multiply any number, this 31 can be any number. If you multiply it with 10, you will place a 0 at its end. This is something you do naturally. And the other point is that you can multiply 2 and 5 and you will get 10, which you can multiply with 31 to get 310. So what I mean by this is that you can pair up any 2 and 5 to get a 10. And if you look at this string of numbers, you have a 2 here, you have a 5 here. You can simply multiply them together to get 110. Then you have another 2 2's here, right? 12 is 2 power 2 times 3. So you have 2 2's there. And you have a 5 again here, because 15 is 3 times 5. So you have a 2 from here and a 5 from here, which leads you to have another 10. There is still 1 2 remaining, but there is no 5 anymore. So you only have 2 10s as a factor of this number. And that means that whatever you get after multiplying this, it will have 2 zeros following it. And that's all there is to this part. You can try out questions in the next session. It will be very, very easy. Moving on. So let's move on to rational numbers. Just to recap what a rational number is. A rational number is any number that can be expressed as P by Q, where P and Q are integers and Q not equal to 0. In fact, in a more strict sense, you can express any rational number as P by Q, where P and Q are co-prime integers. P and Q are co-primes. And just again looking at the properties of rational numbers in their decimal expansion. Rational numbers can be of two types in their decimal expansion. That is, they can be terminating or non-terminating and repeating. That is, say for example, a terminating rational number would be 1.23. A non-terminating repeating rational number will be something like 2.141414, so on. That is 2.14 bar. And just to bring it back to mind, if it is non-terminating and non-repeating, then it is definitely irrational. Do not forget that. Now let us look at a method to use the fundamental theorem of arithmetic to find whether a rational number is terminating or not terminating. For this, we are going to use three examples. Let's say 63 by 60, 128 by 75, and 100 by 77. We are going to proceed through a set of steps with these three numbers as examples simultaneously. So the first step is to write the fraction in the standard form. Do not ever forget this, because if you miss this step, there is a high chance of you getting it wrong. So 100 by 77 is already in standard form, 128 by 75 is already in standard form, but 63 by 60 is not in standard form. They can both be factorized by 3, and you will get it to be 21 by 20. And for the next step, you have to factorize the denominator using the fundamental theorem of arithmetic. If I do that, I can write 20 as 2 into 2 into 5. I can write 75 as 5 into 5 into 3, and I can write 77 as 7 times 11. Now if you look at the next point, or rather the next idea, it is that if the denominator has only 2 and 5, like in this case where you only have 2 and 5, you can conclude that that fraction, that rational number, is definitely terminating. And if the denominator has any other prime numbers other than 2 and 5, then you can safely conclude that it is non-terminating, repeating. And that is the case for both our other examples. Like here you have 5 in the denominator, but you also have 3, which is not 2 or 5. And here you have 7 and 11, both are primes that are not 2 and 5. So they are both non-terminating and repeating. And you can actually easily make out the reason for this to be true. If you remember the procedure to convert a terminating rational number, say something like 1.05, if you want to convert it into a rational number, what you have to do is you can multiply and divide this number by 100, and you will get it to be 105 by 100. Then you can strike off all other factors, and I just took it to be the same fraction here. But the idea is that if you can represent the denominator as a power of 100, like in case of 21 by 20, I can multiply and divide it with 5 to make it 105 by 100. But if I can make the denominator power of 100, then I can show it as a terminating fraction. If the denominator has any other prime number, then I cannot express the denominator as a multiple of 100, and so I cannot express it as a terminating fraction. Now there are actually 3 theorems in your textbook that describe the exact same thing. The idea is nothing different. All you have to, you can just read through them and you will understand it very easily. So the first, in fact, let's actually write it down, where you have a rational number that is p by q, and q, the denominator, is of the form 2 raised to n into 5 raised to m. Now that just means that the denominator can be factorized into a product of only 2 and 5. That is simply what I have described previously. And this theorem 2 here, it says that if this is true, then the number terminates. Just simply what we already learned. And the first theorem simply states the opposite. That is, if a number terminates, then this is true, which is naturally correct. And the theorem 3 is the other part of the theorem, that is, if q not equal to 2 raised to m into 5 raised to n, that is, q cannot be expressed as a product of 2 and 5 only, then it implies that it is not terminating. It's not terminating, repeating. I believe it is clear. Let's move on to the next topic, which is irrational numbers. And the only thing that you have to focus on in this part of this chapter is the proof of irrationality. That is, you already know multiple irrational numbers such as, say, root 2 and pi and e and root, say, 17 or something, root 17 plus 1 by 5. All of these are irrational numbers. But in this chapter, we are going to learn to prove some rational numbers such as root 2 or any combination of these numbers. We are going to prove that they are irrational as well. And that's all we are going to do in this chapter, dealing with irrational numbers. But before actually moving on to the proof of irrationality, you will have to know this theorem. It's not going to be asked for the exams, but it's a very simple theorem. You just have to keep it in mind so that you can actually prove the irrationality. So the theorem says that if p is a prime number and it divides a square, where a is a positive integer, then p divides a. In fact, just to confirm that it can be correct, let's try out an example. So let's say 144 is a square, 144 is 12 square, so a equal to 12, and 144 you can factorize it and you can find out that 3 is a factor of 144. So 144 can be divided by 3. Now you can directly see that 3 is a prime number, 3 is p, and 144 is a square, and p divides a square, 3 divides 144, but p, which is 3, also divides 12, which is a. So it makes sense, but let's quickly prove it. So all you have to do is, you have to first take the positive integer a and express it using the fundamental theorem of arithmetic. That is, you can directly write it as p1 times p2 times p3 times p4 times and so on up to pn. This is just the expansion using the fundamental theorem of arithmetic, where p1, p2, p3, p4 up to pn are individual prime numbers, which are a factor of all the prime number factors of a. So this is the prime factorization of a. And so the prime factorization of a square will be p1 square into p2 square into p3 square into p4 square all the way up to pn square. And this is also an expression that is based upon the fundamental theorem of arithmetic, that is p1, p2, p3, p4 up to pn are the factors of a square. Now we already know from the proof, from the theorem we are trying to prove, that p divides a square. That is, p is one of these prime numbers, since they are the only factors of a square. So p is either p1, p is either p2, p belongs to p1, p2, p3, so on, pn. That is, p is one among the prime factors of a square. Naturally, they are all prime factors of a as well. So p has to be a prime factor of a. Simple as that. The proof you don't need to remember, but the theorem you have to keep in mind, because we are going to use it right now to prove that root 2 is irrational. It can actually be any prime number. Root of some prime number is irrational. Say even root of 31 is irrational, because 31 is a prime. You can use the same method, and this method is called proof by contradiction. It's a very interesting thing to do. Let's look at how to do it. So let's prove that root 2 is irrational. The first statement itself is a little confusing looking. You have to assume that root 2 is rational, and that is what we are going to do. We are going to consider that root 2 is rational. This means that root 2 can be written as p by q, where p and q are co-prime integers and q not equal to 0. That is our initial assumption. Let's say that root 2 is actually rational, and then we are going to use this assumption that root 2 is rational, and then we are going to find out that this can never by itself be true. We are actually going to contradict our own assumption, and that can only mean that root 2 cannot be rational, and if root 2 is irrational, it can only be irrational. So what we do is, again we express root 2 as p by q, where p and q are co-prime integers. They are necessarily co-primes, they don't share a factor. If they shared a factor, we can just cut it. So p and q are co-prime integers. I'll write that down again. P and q are co-prime integers, and so we'll make it out that root 2 equal to p by q, and we'll rearrange it. Q root 2 equal to p, and then we'll square both sides, and you will end up getting this, and you will arrive at this result, that is p square equal to 2q square. Now if you just look at this, q square is an integer, q square is a natural number, p square is also a natural number. So that implies that 2 is a factor of p square. 2 divides p square. And now you remember the theory we just learned, the theorem we just learned, that is, if 2 divides p square and 2 is a prime, so 2 divides p square implies 2 divides p as well. So 2 is a factor of p. And in fact, it needn't be 2 at all. You can actually have, as I mentioned, some 31 or something, and it will arrive at the same result. So p equal to 2r for some integer r. This just means that p has a factor of 2, so it can be multiplied with something else and you'll get p. Obvious. Now what we do is we take this result, that is p is equal to 2r, we'll put it in our previous equation and we'll get a new equation, that is 2r square equal to 2q square, 2r whole square equal to 2q square. That is, you can actually have a 4 and 2 here and you will cut it, and here you will notice something interesting. 2r square equal to q. According to the exact same logic, r square is a natural number, q square is a natural number. So 2 is a factor of q square. 2 divides q square. And using the exact same theorem we just used just a second ago, we can conclude that 2 divides q as well. Now you notice a contradiction. Q is 2s for some integer s, means q has 2s as factor. But now p has a factor that is 2. P has a factor 2. Q also has a factor 2. They have a common factor of 2. But we had initially assumed that P and Q are co-primes. Had they not been co-primes, they can be cut until they form a standard fraction in which P and Q are co-primes. A rational number can be expressed that way. But here we just proved that P and Q has to have the common factor of 2. That contradicts our initial assumption. It just does not mean that P and Q are not co-primes. It means that P and Q cannot be co-primes. And if P and Q cannot be co-primes, then root 2 cannot be expressed as P by Q. Root 2 not equal to P by Q for any natural number P and Q. This means that root 2 is not rational. And naturally it means that root 2 is irrational. Hence proved. To top it all off, we need to do a lot of questions. All of these are simple theories, but to actually drill it in, you have to do questions upon questions. So I'll probably be able to make a session to do the questions. Thank you for watching this video. Again, don't forget to like, subscribe to Stutor. Bye.